let's have a look at data representations in Prolog. Well, of course, in Prolog, all data are represented by terms. So, in a sense, in the terminology of data structures, all data in Prolog are represented by trees, right? But still, we have certain degrees of freedom, and we can choose how we represent our data in Prolog. I mean, it's true that all these representations are eventually terms. Yet, our choice of representation can have significant effects on our programs, and it can influence their performance and even their semantics. And of course, our goal is to choose data representations that make our programs general and efficient. So, for generality, we must keep to the pure monotonic core of Prolog. And for efficiency, we must make our code amenable to argument indexing. And one good thing about Prolog is that generality and efficiency often go hand in hand. So very often, the most elegant and most general code is also most efficient. And both generality and efficiency often hinge on what we call clean representations of our data structures. Clean means that we can distinguish all cases symbolically by the principal functor of the term under consideration. So, for instance, lists are a clean representation, because when reasoning about lists, there are two cases. Either the list is empty, so the atom nil, or the list has at least one element, say L and tail ls. So, importantly, argument indexing can distinguish the cases because they have different functors. Because the empty list is an atom, and a list with at least one element has functor named dot and arity 2. So indexing can easily distinguish the cases, and that's of course good for performance, because it avoids unnecessary choice points and allows fast hash-based lookup. Or as another example, here's a clean representation of binary trees. And I say a clean representation because we can represent binary trees in different ways. And the fact that we use Prolog terms in all these cases does not mean that all representations are equally useful or equally sensible. In fact, quite the contrary. Some representations are much more useful than others and also have more desirable properties. And in fact, finding good representations of the available data is a significant aspect of Prolog programming. So let's consider one way to represent binary trees in Prolog. Let's distinguish three cases. Let's denote the empty tree with the atom nil. I mean nil spelled out, not the empty list nil. Although we could of course use that too. And let's denote with leaf of data a leaf of the tree with associated data. So a leaf is a node that has no children. And let's denote with node of data left and right an internal node with associated data and left and right children. And that's all. So what we have here are three cases that can again be distinguished symbolically, because we have an atom, a compound term with functor name leaf and arity 1, and a compound term with arity 3. So argument indexing can tell all these cases apart, because they have pairwise different functor names and even different arities. And that's of course good for performance. And of course that's not the only representation we could use. For instance, what about leaves? Do we really need a dedicated case for leaves? No, of course not. Because we could also represent a leaf exactly like an internal node that has no children. So both left and right are the empty tree. And that's also a clean representation, because all cases can be distinguished symbolically. Even leaves can be specified symbolically, as we in fact just did here. And depending on the situation, one of these representations may be more useful than others. For example, this representation is conceptually very simple, because it only uses two different functors. However, representing a leaf now takes 4 memory cells. 1 cell for the functor and 3 cells for the arguments. Whereas in the other representation, a leaf takes only 2 memory cells. So the other representation is more space efficient, especially so if the tree has many leaves. And so far, this all looks pretty nice. There may be performance differences, but at least everything we've seen so far are clean representations. And this could be the end of it, were it not for the fact that not all representations are clean. For example, let's describe integer expressions as we know them from CLP-Z. And in fact, let's focus on ground integer expressions, because the problem also arises if no variables at all are involved. So what is an integer expression? Well, let's state it in Prolog. So let's use a predicate, say expression, where we define what we mean with an integer expression. For instance, a plus b is an integer expression. Well, at least if a and b are integer expressions. And that's of course not the only case, because a minus b is also an integer expression. Again, if a and b are themselves integer expressions. And the same for a times b, and also for other cases. And up to here, this is all clean, because the cases are symbolically distinguished by different functors. For instance, here, the argument's principal functor is plus with arity2. And here, it's minus with arity2. And here, it's times. So, argument indexing can easily tell the cases apart if the argument is instantiated. However, we're still missing an important case, because what about concrete integers? And of course, concrete integers such as 1, 2, and so on are also integer expressions. In fact, they are the most basic case, so we better include them. So expression must hold for concrete integers. But now we have a problem, because we can't collectively recognize all integers by a dedicated functor. Because a concrete integer is an atomic term, and so the integer 1 is different from the integers 2, 3, and so on. And these integers have no principal functor in common. So all we can say here is I is an expression if I is an integer. That's really all we can say here, because we can't recognize all integers by a common functor. And if we think about this last clause, and especially about the clause head, then we could call this a default case, because this clause head always applies, because this I here is a variable, and so no matter what the argument is when the predicate is invoked, this clause head definitely applies, no matter where it's placed. So I'm not calling this a default case because it's the last clause in the definition, but because it's so general that the head always applies. So in this sense, we call it a default case. No matter the argument, this clause head applies, even if the other clause heads don't apply. And no matter how we order the clauses. And now we have a problem, because the head of our default clause also applies if other clause heads do apply. So, for instance, in this case, we invoke our predicate with the argument 1 plus 2, that is a ground term, and it's clear that the first clause head applies. And the last clause head also applies. So, two clause heads apply. And so indexing can't distinguish the clauses. And that's of course bad for performance, because a choice point must be created and so on. So, for this reason alone already, we can say that this is a faulty representation, because it impedes performance. And in Prolog, a representation like this has a special name. We say that this is a defaulty representation, which is a play on words that combines default, because our definition has a default case, and faulty, because the representation is flawed. And it's flawed not only because it impedes indexing and therefore performance, but also, and that's even more problematic, it's flawed for semantic reasons. And to illustrate this, here's a thought experiment. Let's consider the term x plus y. And now we ask, which integer expressions are subsumed by this term? For instance, 1 plus 2 is obviously subsumed by this term, because this is a term with principal functor plus and arity2, so the first clause that applies, and the last one also applies, but 1 plus 2 is a compound term, and that's ruled out in the body, so only the first clause applies, and the two arguments of this term are concrete integers, so the last clause applies. So in total, 1 plus 2 is an integer expression that fits this pattern, x plus y. But it's not the only case. And of course, 1 plus 3, 2 plus 5 and so on also fit this pattern. But the key problem with this representation is that there are even cases that are structurally very different from 1 plus 2. For example, the term 1 plus 2 plus 3 also fits this pattern. Because clearly this is also a compound term with principal functor plus and arity 2, and so it also has the same pattern, x plus y. The first clause applies for the entire term. We already know that the first argument 1 plus 2 is an integer expression, and the second argument, 3, is an integer expression by the last clause. So 1 plus 2 plus 3 also has the shape. Or for example, this term. This also has the shape x plus y, because again, it's a compound term with principal functor plus and arity 2, and both arguments are integer expressions. And there are many more cases. So the core problem with this representation is that we can't symbolically express the sum of two concrete integers in such a way that we subsume all and only expressions of this shape. Because these examples all have the shape x plus y, but we can't symbolically constrain the arguments to concrete integers. Because x and y stand for concrete integers and also for compound expressions. And this ambiguity leads to semantic problems in all predicates that reason about integer expressions in this representation. For instance, let's consider equality. If we ask Prolog, is there any x such that 1 plus 2 is equal to x? Then Prolog answers, yes, that's the case, and x is 3 is the only solution. And at first sight, this may seem sensible enough, right? After all, it's true that 1 plus 2 is equal to 3. But on the other hand, if we ask, is it the case that 1 plus 2 is equal to 7 minus 4? Then Prolog says, yes, that's also true. And that seems sensible too, right? Because after all, 1 plus 2 is indeed equal to 7 minus 4. And importantly, the right-hand side here is a compound term with principal functor minus and two arguments. So we know that this answer is incomplete because x is 3 isn't the only solution, because as we've just seen, for example, the compound term 7 minus 4 is a solution too. But the system doesn't report it. Instead, it only shows us one out of many solutions. And moreover, if we now ask explicitly, is x equal to 1 plus 2, if x is the compound term 7 minus 4, using syntactic unification, then the system says no, which is incorrect, because 7 minus 4 is arithmetically equal to 1 plus 2. And interestingly, if we put the unification x is 7 minus 4 in front of the other goals, and then simply repeat what we said above, then it succeeds. So that's correct for a change. And this also means that if we take this query and generalize away the first goal, then it fails again. And this means that the system is no longer monotonic, because by generalizing away a goal, we made a query fail that previously succeeded. So illogically, a supposed generalization is more specific in that it fails. And the reason for all these issues is the defaulty representation of integer expressions, because semantically, variables in CLPZ stand for concrete integers and also for compound expressions. But operationally, the system treats them as standing exclusively for concrete integers. So what can we do to correct these issues? Well, we use a clean representation for integer expressions. So what does a clean representation look like? And if you remember in our definition above, the first three clauses were already symbolically distinguished by the principal functor of the argument. So the key problem was the last clause, our default case, which we used for concrete integers. So to turn this into a clean representation, we need to change this clause. And specifically, we need to symbolically distinguish concrete integers from all other types of expressions. And we do this by using a dedicated functor for concrete integers. And we can use really any functor we want, as long as it's different from the other ones. So, for example, let's use, say, number sign of I. And the body is the same as above. So, number sign of I is an integer expression if I is an integer. And this is of course a compound term with principal functor number sign and one argument, namely I. So the single difference to what we had previously is that integers are now indicated by a dedicated functor, also called a wrapper. And this may seem like a small change, but the consequences are quite profound, because as one immediate benefit, this is good for performance, because argument indexing can now distinguish the clauses by the principal functor if the argument is instantiated. And second, this representation has a major semantic benefit, because we can now symbolically express the sum of two integers by writing number sign of A plus number sign of B. And by symbolically, I mean that the term by itself already indicates the shape of the expression, because A and B must now be integers. So the only thing that's not specified here are the concrete integers that A and B stand for. But we do know that this term is a sum of two integers. And we know, for example, that no multiplication, subtraction, and so on occurs in this term, already by its symbolic structure. So what is this term? Of course, it's simply a compound term. So there's nothing special to this. We have chosen the functor, this wrapper, and we could have chosen any other functor name too. It's completely arbitrary. It only matters that concrete integers are now symbolically distinguished from other expressions. But in this particular case, I chose number sign for a reason, because in CLP-Z, number sign is already defined as a prefix operator. And so instead of functional notation, we can use operator notation to write these terms. So we can simply omit the round brackets here, because number sign is a prefix operator in CLP-Z. And of course also here in the clause head, we can use operator notation. And semantically, the term is of course still the exact same term. We've only written it differently. And as already mentioned, argument indexing can now easily select the single fitting clause for each sub-expression, because for the entire expression, only the first clause head applies. And for both of the two arguments, number sign A and number sign B, only the last clause head applies. So importantly, we no longer have the problem that more than one clause applies in some cases. And in particular, we know in this case that both A and B must be integers and can't be compound expressions. And the really great news is that the clean representation solves all semantic shortcomings we mentioned. So using the clean representation, we write number sign 1 plus number sign 2 is equal to number sign x. So in other words, this is again the question, is there any x such that 1 plus 2 is x? But now it's made clear that we are asking for concrete integers x, not for compound expressions. So we are asking, is there any integer x such that 1 plus 2 is x? And when we post this, the answer is again 3. And the answer also tells us that 3 is the only solution. So what about the case 1 plus 2 is equal to 7 minus 4, which are both compound expressions? Are these compound expressions equal, arithmetically equal, in the sense that they evaluate to the same result? Yes, that's the case. Now, what if we substitute the compound expression for x? That is there any x such that 1 plus 2 is x, and x is the compound expression 7 minus 4, using syntactic unification? No, of course not. Because at the time of the unification, x is the integer 3. And 3 isn't unifiable with a compound term. But what if we exchange the goals? So what if we first say x is the compound expression 7 minus 4, using syntactic unification, and then ask whether 1 plus 2 is x in an arithmetic sense. That's a type error. And it's of course justified, because as just mentioned, number sign is used to indicate concrete integers, and the term 7 minus 4 is not an integer, but a compound expression. And importantly, from a semantic and logical perspective, type errors can be replaced by silent failure, because there's nothing we could add to this query that would make it succeed. So neither this query nor any specialization of this query is satisfiable. And so it would be correct to say simply false, on the grounds that there is no solution. And to allow sound logical reasoning about programs and queries, CLP-Z also supports a monotonic execution mode, where number sign must be used for variables. Because there's still a problem here, since by default, we are not forced to use number sign for variables. So we could, for instance, omit the number sign in this case and get the same solution as above, telling us that x is 3 is the only solution for 1 plus 2. And that's of course again incomplete, because 7 minus 4 and so on can also be substituted for x, since x is now a free variable and stands for any term whatsoever. So the monotonic mode forces us to indicate that we mean concrete integers, because if we enable the monotonic mode, then what happens? Because there are many terms that satisfy this equation, such as 3, 2 plus 1, 3 times 1, 7 minus 4, and also many others. In fact, there are infinitely many solutions in this case. So if the system reports only one of them, or even only a finite subset of them, or more generally leaves out any one of them, then it would be incomplete, because it would fail to report solutions that exist. And that's a complete no-go, of course, because we're usually very interested in finding solutions. And if some of them are omitted, then we can't reliably do that. And at the same time, it would be undesirable to enumerate all solutions in this case, exactly because there are infinitely many of them. And we expect CLP-Z constraints to always terminate, so that we can more easily reason about programs. And as a special case of incompleteness, it would of course be completely wrong to say that there are no solutions. So the system of course can't say false here, because that would mean that there are no solutions when in fact there are solutions. And if you think about it, in a sense, incompleteness is even worse than incorrectness. Because suppose that the system reports a term that turns out to actually not be a solution. So suppose, for example, that in addition to 3, the system also reports, say, 5 as the result of 1 plus 2. Then at least we can test this supposed result and find out that in fact doesn't satisfy the equation. But on the other hand, if the system fails to report terms that are actually solutions, then we see nothing and can't test anything. It would mean that the truth not only remains unknown, which would be acceptable, for example, if the query doesn't terminate, but it would mean that the system misreports the truth. And that's of course the exact opposite of what we want from our system. So in this sense, incompleteness is even worse than incorrectness. And saying false here would be even worse than emitting wrong integer expressions. So in light of these considerations, what is the answer in the monotonic execution mode? It's an instantiation error. This means that the term isn't sufficiently instantiated to say anything about it. And importantly, instantiation errors cannot be replaced by silent failure because there may be solutions. And in this case, if we add additional constraints about x, we also get them. So in the monotonic execution mode, we must use the wrapper for variables, and then it works exactly as before. So clean representations improve performance and allow sound reasoning. And indeed, it's one of the nice attractions of Prolog that efficiency and correctness often go hand in hand, and in many cases, we can't have one without the other. And at this point, you may have a question, namely, if clean representations offer such great advantages, then why do defaulty representations even arise? And there are several reasons for this. First, defaulty representations are sometimes easier to read and write for programmers and also for users. For example, this integer expression uses a defaulty representation. And here is the corresponding clean representation. And as much as I like and prefer clean representations for internal reasoning within Prolog code, I'm not going to argue here that the clean representation is easier to read, let alone write, than the defaulty one. However, we're still free to use clean representations internally. So maybe we'd like to offer users the ability to enter expressions in a defaulty form, because that's what they are used to, and at the earliest opportunity, we can convert the expressions to a clean representation, so that our programs are more general and also more efficient. And when emitting such terms to users, we can easily use a defaulty form again. So that's one way out of this situation. Then sometimes defaulty representations arise simply because they are required due to the way exercises that are given to students are formulated. For instance, let's write a simple set solver in Prolog. So we'd like to relate a propositional formula to its truth value. For instance, true is true, as the name suggests, and false is false. So we relate here syntax to meaning, also for compound expressions, such as conjunction. The truth value t of the conjunction a and b depends on the truth at of a and so on. Likewise for disjunction and so on. And variables can of course also occur in the formula. And by variable we mean either true or false, not a compound expression. And here we have a problem, because we already see from the clauses so far that this is a defaulty representation of formulas, because this clause head always applies. And so we have the usual disadvantages. It prevents argument indexing, and we also run into the semantic problems we've seen. Because if we commit to any of these cases, even when two or more apply, then we destroy monotonicity. And the solution is of course to use a clean representation instead. For instance, we can indicate variables with a wrapper v, say, for variable. And of course we can place the clause anywhere we want. So in this case, a better place might be here, for example. And recent CLPP systems already do support this wrapper and also provide a monotonic mode where we must use the wrapper for variables. So for exercises, I recommend to use clean representations in the first place, because a clean representation gives a much better impression of Prolog's capabilities and generality, and it's also easier to handle. And sometimes defaulty representations are used for backwards compatibility. Most notably, Prolog code uses a defaulty representation. And let it sink in for a moment, and also what does this even mean? Well, a Prolog clause has the form head is implied by body. And what is body? Well, let's define it in Prolog. What is a clause body? So certainly true is a clause body, right? For example, a Prolog fact is like a rule where the body is true, because a fact always holds. And then there are other cases too. For instance, a clause body can be a conjunction of goals. And of course, a conjunction is only a valid body if both conjuncts A and B are bodies. And further, a body can also be a goal that is different from true and different from a conjunction. So now we have a problem again, because here we have a default case again, with the usual drawbacks. For instance, when we ask, is the conjunction true and true and true a body, then the second clause head applies, and the third clause head also applies, because the third clause head always applies. So we are again in a situation where two clause heads apply, and so indexing can't distinguish the cases and so on. So the core problem with this representation of Prolog code, and this isn't just any representation of Prolog code, because this syntax is prescribed by the ISO standard. So the core problem is that goals can't be symbolically distinguished from other constructs, because goals don't have a common functor. And this situation could be aptly called an ancestral fault, because this is the situation we are facing with the existing standard. And of course, we could easily correct this simply by using a clean representation. So, as in all the other cases we've seen, we can solve this by using a wrapper for goals, so that all goals have a functor in common. For instance, let's use the prefix operator plus to indicate a goal. So instead of just plain goal, the term plus of goal shall indicate a goal. And this idea was in fact used in the intended successor of Prolog, Prolog 2. So in Prolog 2, all concrete goals are indicated by the common functor plus. However, this idea hasn't caught on, or at least not yet, because who knows what the future brings. So, at least for now, we are stuck with a defaulty representation of Prolog code, at least when reading it in. Because we are of course free to internally convert the defaulty representation to a clean one. And indeed, it usually pays off handsomely to do this, because a clean representation is much easier to reason about. For instance, take the first clause of our expression definition. So this is the usual and defaulty Prolog representation. And if we want to run the program, we must of course use Prolog syntax. However, to reason about the program, we can also write it differently. For example, by writing the body as a list of goals, which is a clean representation. So we can simply write the clauses in this different form, or internally convert them to this form. And of course, we can now no longer run them directly as Prolog code, but we can reason about them much more conveniently. And it's also trivial to generate Prolog code from this representation. And we can also easily tell that this is a clean representation because we can now specify the shape of a body without specifying any concrete elements. For instance, we can symbolically specify a list with 2 elements, and it's clear that we mean 2 goals in the body. So there is never any ambiguity about the number of goals or where the concrete goals are in the term. And that's in contrast to what we had in the conjunction example earlier, where we couldn't symbolically limit a conjunction to exactly 2 goals. And therefore, the clause for 2 goals also applied for a body with 3 or more goals. And we had to use a default case for concrete goals. So the main takeaway of all these considerations is the strong recommendation to use clean representations, either right from the start or at least internally by converting defaulty representations to clean ones. And Prolog implementers can, and of course should, promote the use of clean representations in the system's interface predicates. For example, consider copy term, which lets us reason about constraints a variable is involved in. So if we have a few constraints, then copy term takes a term, creates a copy of the term, which can also be the same term, and in the third argument yields the residual goals that are equivalent to the posted constraints. So for instance, we may get this answer. So we get a list of residual goals. And as mentioned, a list is a clean representation. And we can, for example, use maplist to invoke these goals. And it's easy to reason about lists because there are built-in predicates, DCGs and so on for that. And while newer Prolog systems do use a clean representation for this, that's not a given. And there are indeed systems that use a defaulty representation here, because as in the defaulty representation of Prolog code, one could, for example, use a conjunction of goals and represent, for example, 2 residual goals as G1 and G2 using a comma. So that's of course not a list, but it's at least arguably some form of sequence, and such a representation is also called an AND list, because it's a conjunction of goals. But we know, of course, that it's not a list, so instead of G's, let's write G, because the entire term can in fact be regarded as a single goal, using the built-in predicate comma with 2 arguments. And we can easily invoke such a goal, using the built-in predicate call, because G is already a goal and can be called right away. But reasoning about G is not convenient and also not efficient, because when we analyze such goals, we always run into this ambiguity between conjunctions and atomic goals. And atomic goals have no functor in common. So this is an example where a representation may at first seem convenient, because we can, for example, so easily combine two goals using constant time concatenation, but where it turns out that it complicates programs a lot and also results in the same semantic issues we've seen. For example, that we can't symbolically specify the general shape of such conjunctions. That is, defining the outline while leaving the concrete elements unspecified. Well, we can try, of course. So, for instance, let's consider the conjunction G1 and G2. How many goals are in this conjunction? At least 2, right? But could there also be 3, 4, or more? Yes, because this shape, of course, subsumes true and true, for example, and also true and true and true, and also others. And another way to see that this is defaulty is that there's no way to unambiguously express an AND list of AND lists. And again, we can try, of course. So for instance, this may seem plausible enough at first as an AND list of 2 AND lists. But there's a clear problem here because, for instance, if the second AND list only has one goal, say C, then that's the same term as a single AND list with 2 goals. So we can no longer be certain whether this is an AND list of AND lists or simply an AND list of goals. And the main problem when using defaulty representations in system interface predicates is that they affect all user programs in application code. So such a choice by an implementer means that everyone who's seriously using the interface must work around the defaultiness and convert it to a clean representation. Because what's the alternative? The alternative is to pass around a defaulty term and run into the same problem over and over and over in all predicates that reason about it. And of course, these issues all go away with a clean representation, such as when using actual lists of goals. So it's for the best that we forget the defaulty representation again and consider a second example of a clean representation, namely delimited continuations. And without even having to know any details about it, the key point here is that 2 cases need to be distinguished. Either there is no continuation or there is a continuation. And if we represent the cases like this, then this is clearly a clean representation because the principal functors distinguish the cases symbolically. And for example, Scryer Prolog does use a clean representation in this case. And such interface predicates are good examples of what progress means in Prolog systems, because in both cases, that is both for copy term and for delimited continuations, there are also systems that do it differently and use defaulty representations, whereas especially newer Prolog systems often take the opportunity to move towards clean representations. So progress in Prolog systems also means that systems become more convenient to use and preserve interesting logical properties, such as monotonicity, which is needed for automated reasoning about programs. And convenience and logical soundness often start by choosing clean representations. So using clean representations is a really important part of Prolog programming. And as we've seen, it's good for semantic reasons and also for performance. And it's not a given, because Prolog doesn't enforce clean representations. So to avoid defaultiness, we have to actively choose a good representation. So maybe I should phrase this a bit differently and say that Scryer Prolog already uses a clean representation, because this is the direction where I hope more Prolog systems will go in the future. And Scryer is simply the first in this specific example. And importantly, there is no shame in improving things. So Prolog implementers can use such opportunities to also improve their systems. Of course, it can be painful for an implementer to break backwards compatibility, but in the long run, that's just temporary. And application programmers are generally also very accepting of changes that are improvements. And a clean representation, once it's there, is great for the entire future of the project. So even if changing an interface predicate means breaking things now, it also means much greater benefit for all users in the future.